Before I end this video, I'd like to have a look at example 12.12. It's on page 644, and this is the problem that they have. They say, is it possible to predict graduation rates from freshman test scores? And these freshman test scores that they're referring to are SATs. So the reason why I wanted to look at this example was to show you how you do this example in R. In the textbook, they give you output for SAS, but we are not doing SAS anymore. We're using R. So I wanted to show you how you do it there. So in other words, what they're asking you to do is to look at this variable and this one, and then we're going to determine whether there is any sort of a linear relationship. So the first thing that you want to do whenever you get any data set that you want to fit a model to is you want to plot it. So you'll see in your textbook, they did plot it on the next page. And if you try to plot it in R, you'll get something that looks like this. So when you look at it, you want to see, does the data more or less give you some sort of a straight line in terms of the relationship? So you can see here that you have this positive slope. It's going upwards, and maybe you could fit some form of a straight line in there. So this would be your first indicator that a linear regression model it might be appropriate for this particular data. So now let's have a look at the R code and run it. This is my R code that I have. So the first thing that I want to do is to upload my dataset. So it's saved in a .csv called university. So you're going to use read.csv and then type the dataset in. And I've stored it in a variable called university data. Now, what I like to do is every time I do something, anything I do, I like to print everything line by line so that I can see, and I make sure it's visible. So I'm just going to remove this so that you can all see what happens if without the brackets, just for those of you where it might be new. So if you run this line, it uploads the data and you'll see in your environment it will be there. But if I want to view it in here, then one way I can do it is I could type either in the console here and then it'll show me. Alternatively, I could have it here and then run that line and then it'll show me the data. But the easiest way would be to put it just in brackets and then it automatically prints whatever in there. So I highly recommend that you print everything as you go along. And then now I'm sure that, okay, my data is correct. So remember I showed you a graph, a scatter plot of the SAT scores and the graduation rates. And this is the line of code that I use to do that. So the first thing though you need to do is determine which axis does everything need to be. And you're going to have to refer to the question. Here we were asked, is it possible to predict graduation rates from freshman SAT scores? The function that you're going to use is going to be this one, and we'll come back to it. The first thing that we need to do is identify x, which is our independent variable, and y, our dependent variable. And then here, these are other terms. Remember, sometimes your independent variable is also called your explanatory or predictor variable. So you just need to ask yourself which one is influencing the other. And in this case, we're trying to investigate whether y is being influenced by X. So in other words, whether graduation rates are influenced by freshmen's SAT scores. So if you look at this example, SAT scores will therefore have to be our explanatory variable, and then graduation rates will be our response variable. Okay, so back to our plot. So on the x-axis is where I wanted to put my SAT scores, and the y-axis needed to have the graduation rates. And then the other information here is just the title that I added, then the label for the x-axis, and then for the y-axis. So what you could have done, you could have assigned this data to a variable and put it in there, but I wanted to do it in one line. But if I take that, I just copied it, Control C, and then I paste it in here, and then I just run it. I can immediately see that what's contained in here is what I want it to be. So I can see here 1465 is the first value, all the way to the last value are there. And you can do the same thing for the other one as well. So just be printing everything line by line. It's good practice and it helps minimize errors. So I know now the data stored in these two variables is correct. So when I run this code, it produces the plot that I showed you earlier. So it's always good practice to run your R script line by line. So remember, R always runs where your cursor is. So if I click on run, it runs that line. So that's in my plot window, but we've already looked at that. And then now for the model, you use this LM function. I think it's short for linear model. And then remember, this is the formula. You'll have your Y variable first, and then this is tilde. So if you look on your keyboard, you'll just need to see where you can find it. And then X is going to be your value, your data for your SAT scores, because we already identified that SAT is that. And then here, my data, this is my DF is just short for data frame. So this is where your data is contained. So in other words, in our case, it's this variable university data. And then for Y and X now, I can refer to columns in that data frame. So if I wasn't sure what the column names were, then I would just type names, and then the variable in the data in this case is university. It's popped up there. So I just started typing and it popped up. And then if I run this line, I can see that I have these columns: rank, university, grad rate, and SAT, etc. And the ones I want here are this grad.rate and SAT. So remember, grad.rate is my Y, so I write it there, and then SAT is the one there. So it already knows that we're in this data set, so it's just referring to those columns. So once we've put in the columns we're interested in, we're going to run that line. It's not necessary to print that. In order to see the detailed output, you'll now click on you'll now run summary and then put the model in there. So this model is copied in there. So if I run that line, then it gives me this output here. So it gives me what I typed, and then it gives me these different statistics for the residuals, the minimum, my median, quartiles, and then this is the important output, which I'm going to look at in detail with you just now. And then for the ANOVA table, remember where we had the F-test statistic from the model utility test, you will do AOV, short for analysis of variance, and then you'll put the model in there again, and you'll click on run. And then, click on run. I had only highlighted model, so it was just trying to run model on its own. So this is the output here below AOV that you will get. And this gives you your sum of squares that you can put in your ANOVA table. Okay, so let's refer back to the slides and then I'll show you what's what in this output. But this is the basic code if you want to do regression. It's very easy. You just do your model using the LM function, and then to get your regression model and any sum of squares, you'll just type summary and then the model and AOV and then the model. This variable, you could have called it anything you want. I chose to call it model. You can call it anything you want to. So let's go back to the slides and have a look at the output in more detail. Since Chapter 12 is not included in your practical test, you don't need to worry about being able to do the coding in R. However, you can be given R output in a semester test or an exam, and then you need to be able to know how to interpret the values that you are given. So I'm going to spend a little bit of time just showing you what's what. This can be easy marks because all the values are really calculated for you. So in this output, the first thing that we have is the model. So remember, we had our graduation rate and SAT. So remember, Y came first and then X. So in other words, the model, I'm going to use GR for my graduation rate. The line that we're trying to estimate is GR equal to beta 0 plus beta 1 times my SAT score. Okay, so in this first little block here with the residuals, they're giving you basic statistics about the residuals. They give you a minimum, maximum, medium, etc. the important information starts now here with your coefficients. So that row that says intercept, it refers to things or values to do with beta 0. And then the second row, SAT, is to do with beta 1. So remember, SAT is the coefficient of beta 1. So now if we go and we look at now the next column where it says estimate, this is where you now have your estimate for beta hat 0, and this is where you have your estimate for beta hat 1. So if I asked you to give me the estimate for the linear regression line, so I'm going to refer back to y, then it would be minus 36.18303 plus 0.08855x. Okay, so notice I put the hat because it's an estimated line on the y. Okay, and then remember x is your independent variable, so you'll be putting in values there of your choice. Okay, so now in the next column here where you have your standard error, so you remember your standard error is just your standard deviation of your estimator. So in other words, this first one here, because it's row 1, it's S of beta hat 0, and then similarly, this is S of beta hat 1. So now if you wanted to calculate something like your test statistic, you could do it using this data. So remember, for the model utility test on page 645, you're testing whether there's a linear relationship or not. So it doesn't matter whether it's positive or negative. The question is just, is there a relationship? And then the test statistic is now this value. So if you were to take that beta hat 1 and put it in there, and the S beta hat 1, and also put it in this formula, you will now get this test statistic value here. That is going to be your T. So for this question, it'd be 7.22. The other T value is actually the null and alternative, that beta 0 is equal to 0. But, you know, we're not usually very interested in the intercept, but if you were, you'd do that hypothesis test. So I'm going to ignore the top row now since our focus is more on that slope, because that's the one that measures whether we have a relationship or not. Now, so remember, it's doing the model utility test. So for the p-value, this is what we get here. Remember, you're going to find the probability to the right of 7.22, and then you'll multiply it by 2. So let me write that down for you quickly. So I recommend you do it in R to get the exact value. So you're going to have, you want to find the probability that T with n minus 2 degrees of freedom, I'll come back to that, is greater than your test statistic, which is 7 to 2. Yeah, I should perhaps maybe use a capital T since it is a random variable. So you want to find that probability, and then remember it's two-sided, so you'll multiply it by 2. So this is something that you can do in R, and then you'll see what value you get. I'll show you the value just now. So in this case, you can immediately see that for almost any alpha value, even really small values, you end up rejecting the null hypothesis. Because remember, you will always reject when you have your p-value less than alpha. And in this case, my p-value is actually approximately 0. So if you look how tiny, 1.02 times e to the power minus 0.6. It's a really, really small number. So you're going to reject. And in other words, you'll say that there is enough evidence to conclude that there is a relationship. Okay, so now that you found all those values, if I had asked you to calculate a confidence interval, then you'd be able to find your beta hat 1. We've been given there. And then you'll be able to find your S beta hat 1 from the output there as well. And then for this value, if it will be a value you can find in the table. So like 95% or 90%. Okay, so you'll be able to find that value in your tables. Remember, we also spoke about what's called the coefficient of determination, or in other words, r squared. And it's given on page 634. If you look here, I've given you the formula r squared. Remember, r squared tells you the amount of variation accounted for by the model. And that's the formula. We'll come back to it, but it is given here, and it's given as a decimal. So this answer is actually 74.33%. Okay, so that's where it comes from. Adjusted r squared uses a different formula, so don't use that one. And then remember, you can use a t-test or an f-test to do the model utility test. So this is the f-test statistic, and then these are the numerator and denominator degrees of freedom, and you see the p-value is the same value as what we got with the t-test. Okay, and remember, we said that the t-test statistic is equal to, if you square it, it's equal to the f-test statistic. So you can verify for yourself that 7.22 gives you 7.22 squared gives you 52.12, or at least it gets close. There might be decimals missing if there was any rounding. Okay, so now if you look at the ANOVA output, here in the ANOVA output, we have our sum of squares. So remember our residual sum of squares. If you check on page 631, it is the same as SSE. So just go to page 631. In the block where they define SSE, they write in black brackets that is also called the residual sum of squares. Okay, and then now for the SAT one, that is actually your SSR. And then below here, then they have the degrees of freedom for SSR, and then your degrees of freedom for SSE. And if you wanted to now calculate your r squared, remember this is your formula. So SSE, you have it now. And then to get SST, remember it's just SSR plus SSE, and this is what you'll get. And if you put it in your formula, you will then get your 0. This value will give you 0.7433. Okay, so it corresponds with that. Okay, and then they also give you the residual standard error once again, that 10.29 that we saw here. So if you go to your output, now your textbook, you can compare everything. So you'll be able to see that we got the exact same SST and the same SSE. The estimates, I think we don't have as many decimals from the output, but these are the same estimates. And you can verify everything. Remember, S is 10.29. We saw that already. And then we saw this S of beta hat 1. If we go back, is 0.1226, which is exactly what they have. 0.01226, I mean. And then if you wanted to calculate your confidence interval, remember it's just your beta hat 1, and then you have your t. This is t alpha over 2 n minus 2 degrees of freedom. So it's that value here, okay? And then this is your s of beta hat 1 in there. And that's what's going to give you your confidence interval. And if you look at the conclusion, now that you have this confidence interval for beta hat 1, you have an estimate. And basically what it means is here, with a high degree of confidence, remember it's 95%, we estimate that an average increase in percentage graduation rate, the average increase will be between 0.63 and 0.114 for a 1 point increase. So then you'll see in the next line, they multiply this by 100. So if you multiply this by 100, then you will get what they have in the next line here. So they're just pretty much saying that for a 100 unit increase, then this is going to be your increase now. So it's just 0.63 0.063 is just 6.3, and this one, it becomes that times 100. So everything is just multiplied by 100 to get that statement. And then lastly, for my ANOVA table, if I ask you to complete the ANOVA table, so remember my degrees of freedom is always 1 for SSR, we already have it. And then for the error, remember it's that residual one, it's 18. And then that means n minus 1 is 19. So remember n is equal to 20. And then for my SSR, you just copy it, 5520.511. And then the one for your residuals is your SSE, 1906.439. And then SST is just the sum of those two things, 7426.947. And then remember to get your mean square. Mean square is just a sum of square divided by degrees of freedom. So here, if you take your SSE and then divide it by n minus 2, which is what you have here, then that's what will give you your MSE. Okay, I don't know if I mentioned it earlier, but sometimes when you once we've divided SSE, we can also call that whole thing MSE. So MSE is just SSE divided by its degrees of freedom. Okay, but I think you've seen that in ANOVA already. And then to now get this value here, you'll just divide these two things here, and then that's what will give you your F test statistic value for your hypothesis test. And remember, this one is a one-sided test, so you need, it's not a one-sided test, rather, I mean you reject for large values of F. Okay, so it's still the null and alternative beta 1 equal to 0 versus beta 1 not equal to 0, but you reject for F values that are greater than or equal to F alpha 1 degrees of freedom n minus 2 degrees of freedom there. So that's what I meant to say. Okay, so that brings me to the end of this section. I hope everything made sense. Please don't hesitate to consult if you need any assistance.